wants the slide can check that one. Okay. Kishor can start. Okay. Sorry, we can hear you, I think. Could you check the input, sound input?
Can you hear me now?
Oh, yeah, cool.
Okay, perfect. Yeah, sorry. So yeah, I think let me just make sure if yeah, I think everything fine. Yeah, so thanks Zin, and thanks everyone for making it to the second session. And today I will like try to talk about basically Tori code. And yeah, so we will start with a recap of like what happened last week, and then I will discuss this important code called Tori code. We will talk about how to do error correction via Tori code, and very briefly the Tori code Hamiltonian, and then we will summarize it. So we will go slowly and try to understand it, and later actually we will try to uh, like try to understand some of these things from topological point of view. So I think in future in one of the sessions we will talk about like topology in detail. But you will see that some of the ideas are like already kind of present here. So like um, I think without even talking about topology, some of the insights you can already see here. So let's just recap from last week, like just in case, like people already forgot or something. So last week, like we started with a classical 3-bit repetition code. And then we talked about quantum 3 qubit repetition code. And we had code words, for example. So code word here was that, the 0 logical was 000, we were repeating, and 1 logical was 111. So it was 3-bit repetition code. So we were repeating 3 times. In the quantum case, the 0 logical was, 000, and 1 logical was 111. And then any quantum state alpha 0 plus beta 1 was alpha 000 plus beta 111. So the space which is spanned by 000 and 111 that contained the error-free, like encoding of the quantum states. Okay. Then we talked about errors, and here we had bit flip error, and the bit flip error was that, let's say you start with 000 and let's say this bit flips. So it was 100, for example. But here in the quantum case, you had bit flip as well as phase flip. So quantum in that sense is a bit different. Then for error detection, what we were using is that, like we were just looking at bits and whether bits are, like different. So if the bits are different, yeah, so you just look at, the bit strings, and if let's say the bits are different, then that means, like some error has occurred. That's what here error detection was. And for quantum case, you cannot measure because measurement will disturb the quantum state. So what you do is that you measure parity. And so some symmetry. So for example, we could measure Z1, Z2, and Z2, Z3, and let's say Z1, Z3. And that could tell us like what was the error. So so in that sense, error detection in the quantum case was different. For error correction, we just took majority vote here, and majority vote was like good because I mean that helps us, let's say for example, error correct in the classical case. In quantum case, because once you figure out what error has occurred, you just apply the same operator. And this could work because polys are self-inverse. So if let's say you have some error corresponding to some poly P, and then you apply it again, then because P square is identity, like everything just works fine. Then logical operator was that you had encoding, let's say 000, and logical operator with the not logical will take 000 to 111. And similarly, if you do not on 111, then that will take you to 000. Here we had, like XXX, which can take your 0 logical to 1 logical and 1 logical to 0 logical. And then there we had, ZII, let's say, for example, which when it acts on 0 logical, it gives, like the plus phase. On 1 logical, it gives you minus phase. Then the core distance here was 3. In quantum case, you had to look at, like both Z distance and X distance. And the X distance was 3, the Z distance was 1. And because we look at the minimum of 2, I mean, effectively the distance was 1. So this code was 313 code, like this is how we denoted. And in the quantum case, we had, like 311 code. And some of you have been talking about, here we use single bracket, and here we use like, double bracket. So this might give you, like a summary of quantum versus classical case. Okay, just some of these things so that I can see people. Okay. Okay, perfect. So basically, so this we studied last time, like this classical 3-bit repetition code, and then quantum 3-qubit repetition code. Then we studied, like this formalism, which was stabilizer formalism. And for that, we started with, like some code word basis states. And then we had set of poly operators which leave all code word basis states invariant. Let's say, so we had, like all those PK in S. We call the group of such polys, we call that, like as stabilizer group. And by measuring stabilizer operators, we saw that you can detect errors. And when you measure stabilizer operators, you can get, like +1 or -1. And by measuring different generators, you had like, a string of 1 and -1. So that string of 1 and -1 that you get, that is what people call, syndrome. So it's outcome of the measurement of a given stabilizer generator. So let's say you have syndromes, like, bunch of generators. And that gives you, like whether some error has occurred or not. And by looking at these syndrome values, you try to figure out, like what error has occurred. Okay. And then you error correct. Also, we looked at this relation, which is k equal to n equal to m plus k. So you have, let's say, k number of logical qubit, n is number of physical qubit, and m was number of stabilizer generators. Then n was equal to m plus k. And this was also very easy to see, because let's say if you have n qubit, then the size of the Hilbert space is 2 to the power n. And every stabilizer basically breaks your Hilbert space in 2 parts, corresponding to +1 subspace, -1 subspace. So if you use one stabilizer, it will break it into like 2 parts. If you use 2 stabilizers, then you can partition it into 1, 2, 3, 4 parts. If you have m stabilizers, then like you partition it into 2 to the power m different parts. So you start with a big space and you keep on partitioning, like, with every stabilizer, you partition it in half, 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 half. And you do it m times, so it, like the effective space that you are left with is 2 to the power n by 2 to the power m. And that's where you have, like k logical qubits. So you have 2 to the power n by 2 to the power m equal to 2 to the power k. And then from here, you can take log and you can get n is equal to m plus k. Okay. So we looked at this one. And then we saw that, like let's say, whenever you have a logical operator L, you can have another logical operator LSJ, where SJ is a stabilizer, which will have the same action. And the reason is that, let's say if psi is some code state, and let's say you act by L, then you get L psi. But if you act with LSJ psi, because SJ psi is psi, you get L psi. So you have equivalent set of, like logical operators. And then we looked at, like distance, which was weight of the minimal weight logical operator. So that was the distance in the formalism. Okay. So we studied these things last time. And yeah, and the logical operator must belong to centralizer of the stabilizer group, because it has to commute with all the stabilizer elements. Like it should not take you outside the encoded subspace. So it has to commute with all the stabilizer element, but it should not be a stabilizer. So what you do is that, given your stabilizer group, you try to find the stable centralizer and then remove the stabilizer from it. And all the operators that you are left with are basically logical operators. And the weight of the minimal weight logical operator gives you distance. So, so this is all, like, a summary of what happened last week. Today, we will study the Toric code. Okay. So as we said, like let's say if you have any question or something, like you can ask in the chat box, and those people who know, they can answer. So like in this way, like we can proceed. And also there is Discord where like more such discussions can happen. Okay. So now let's try to study the Tori code. So it's an example, it's a simplest example of this thing called topological code. And actually in future, like, in the future sessions, we will go in detail about, like what are topological codes. So we will try to understand topology, and then we will also try to apply those topological concepts like homology and cohomology to better understand topological codes. And Tori code is one of the first, or let's say the simplest example of topological code that you can think of. Today we will talk about Tori code, but nowhere we will, like talk about anything topology, anything about topology. But some of the insights from topology you will see already, they are present here. And later, when we will discuss topology, we will come back to this example and like try to connect the like pieces. So in the torus, you see that like there are two kinds of loop. There's one loop like this, and there's another loop like this. And these two loops cannot be deformed to a point or to each other. So these loops are called like non-trivial loops. On the other hand, you could have some loop on the surface that you can deform. So these are called like trivial loops. So they are trivial in nature. Tori code is one among many inventions by Kitaev, who is one of my personal hero, let's say, in quantum information. And I believe many people in quantum information and computing think the same. So he has contributed to many topics. So, so in Tori code, basically you have code on a toric lattice. So you have like you have basically like this periodic boundary condition along this direction. So like this you identify with this you identify with this. So you wrap like this. So you wrap this like this, and then here. So you identify this one with this one, and you identify this edge with this edge. And when you do this, you get a donut shape object. You get a like torus. So basically the qubits, they live on the edges. So you notice that you have three kind of object here. For example, on the we take an L cross L grid, and this is what we call like edge. This is what we call a placate, and this is what we call a vertex. So you have a 0-dimensional object, which is a vertex. You have 1-dimensional object, which is called an edge, and you have a 2-dimensional object, which is called a placate. So you have three objects. And then we have periodic boundary condition here, and the qubits they live on edges. You know. So let's say, for the Toric code, we try to study it, within the stabilizer formalism. So we will try to see what are N, K, and D for Toric code. So we take a L cross L grid, and every qubit, qubit, basically each edge correspond to a qubit. So each edge correspond to a physical qubit. So how many total physical qubits you have? The number of total physical qubit will be number of edges. So you have total, like L1, 2, 3, L times L edges coming from, columns. And then similarly, L times L edges coming from the row. So you have total L square from column and L square from row edges, total 2L square edges. So if you take a L cross L grid, you have 2L square edges. And because each edge correspond to a physical qubit, the number of physical qubit that you have is 2L square. So for Toric code, N is basically 2L square. Now one can ask what is K and what is D. So that we will try to see. So we need to find, like what are the stabilizer generators, like, what is the stabilizer group? And there are two kinds of a stabilizer generator in Toric code. One which correspond to these two-dimensional objects, like called placate. So corresponding to placate, you can get this placate generator, and the other corresponding to vertex, so around a vertex, you basically act with X on all the qubits, and you call that, like a vertex generator. And let's say, and if you take a face, and around that, if you act with Z, then that you call, like a placate generator. So for example, here, given a placate P, you take a tensor product of all the ZK, where K belongs to, like, let's say some placate. And here you do, like tensor product of all the XL, where, like L is, like around some, like L is in the neighborhood of some vertex B. So here, for example, you can call it, let's say this is 1, this is 2, this is 3, then 4, then see X1, X2, X3, X4, like that's how you will call it. So you have two kinds of generator. One is placate generator and the other is vertex generator. Placate generator is tensor product of Z. Vertex generator is tensor product of X operators. Now it's a very simple claim that, placate and vertex operators commute. And that's very easy to see, because let's say you have X generator and then you have Z generator, let's say the vertex and the placate generator. Either they will not share anything in common, then in that case, obviously, like they will commute. Or if they share any qubit on which, let's say if they overlap on any qubit, they will always overlap on, like even number of qubits. So let's say here you get, like this placate. So let's say I'm interested in the placate here, then, like I will have Z here, Z here, Z here, Z here. And because 2X and 2Z, like basically the tensor product of X and tensor product of X with itself, like XX and ZZ, that commutes, the placate and vertex operators will commute. And the proof is very simple, that, like whenever you construct, let's say a placate, the maximum they will always, placate and the vertex generator, they will always overlap on even number of qubits. And on even number of qubits, if you have X and Z, that will always commute. Hence, placate and vertex operators, they will always commute. Okay. So this means that, this we needed, because otherwise, how can you have a stabilizer group? Because for a stabilizer group, all the stabilizer elements generator, they have to commute. So all the Z will commute, all the X generators will commute, but the Z generator and X generator also has to commute to have a stabilizer group. And obviously they will commute because they will overlap on even number of qubits. and hence they will commute. So we get a stabilizer group formed out of plaquette generators and vertex generators. Very nice. Now, when you take a plaquette generators, let's suppose, and you can multiply them, and you can get, like, I mean, you can generate the whole group of, let's, I mean, other elements call, like uh, this plaquette operators. The plaquette operator, they will either share a boundary or either will not share a boundary or will have only one shared boundary. And when you multiply them, the resultant operator will include Z operator that act on the boundary of the combined plaquette. Now let's try to, like understand, like, this statement. So let's say I have, like, let's say one plaquette here, and I take another plaquette here. So when I multiply the two, let's say when I multiply this and this, on this common Z, I multiply Z with itself like 2 times, and that becomes identity. So the multiplication of this plaquette generator with this plaquette generator will give me, like, will give me something like this, right? Because on the common boundary that they had here, like, they basically, when you multiply Z with itself, you get identity, and hence, like, yeah, like that basically vanishes. So it's like kind of, you can think of merging of amoeba or something like that kind of thing. Like if you try to visually make sense of it, like you have a very complicated, let's say, one plaquette operator, and let's say you take another plaquette operator, the resultant operator will be, like the common boundary, because here when you multiply, like you get identity. So because you get identity, like this part is gone, and you are left with, like common big boundary. So whenever we multiply plaquette operators, the resultant operator will include Z operators that act on the boundary of the combined plaquettes. And yeah, so I hope this makes sense. Yeah. And the reason is that, Z times Z, like Z square is identity. So whatever is the common boundary on that, when you act with, like Z 2 times, it just vanishes. So the size of plaquette just increases. Okay, so I hope this makes sense. And it could be very much possible that, you have one plaquette operator like this, another plaquette operator like this, and when you multiply them, because nothing is in common, like, yeah, I mean, you just get the product of this plaquette operator. But if they have something in common, like let's say if you multiply this plaquette operator with, like this plaquette operator, yeah, the resultant operator will be, like just this, because whatever you have in common here, this part, like at all the z that you have, like, because Z square is identity, like this part does not matter. So what you are left with, like this big object. Yeah. And yeah, so I try to emphasize it. I mean, it's I mean, it's very simple because, polys are self-inverse. So let's say if you multiply all the generators, so when, let's say, like, I mean, now you can play the game, this game. Let's say I take one generator, I take another generator, I multiply them, and then I get this big object, and then with this object, if let's say if I multiply another generator, then I get this big object here, right? But because, let's say, if I keep on multiplying everything and I have periodic boundary condition, when I multiply all, I get identity, because everywhere now you get, like say, like you yeah, like you multiply Z even number of times. And because of this constraint, you can say that not all placate generators that I have are independent, like there is a constraint. So I had, like total L square placate generators. And there is one constraint. So the number of independent placate generators will be L square minus 1. Because there is one constraint, and that L square, like, different generators corresponding to, like each of these square, like, 2D of faces. So there are L square of them, and there is one constraint. So L square minus 1, that's like, number of independent generators. Okay. And what you can do is that whatever analysis you are doing for, like, let's say primal lattice, I mean, you can go in another lattice called dual lattice, where you interchange placate with vertices and you reorient edges accordingly. So you see that, like I have this lattice, and then there's another dashed line going on. So you can make a lattice out of these dashed lines, and that is called, like dual lattice. So the placate operators are vertex operator in the dual lattice and vice versa. And basically, why we are talking about it is because, let's say if you study placate operators, then you effectively have knowledge of, uh, the the vertex operators on the dual lattice. So we are working with, square lattices, and for a square lattices, the dual lattice is also a square. So such kind of lattices are called self-dual lattices, where, the primal and dual lattice, they are same. If you work with the hexagonal lattice, then the dual lattice is triangular. So they are not self-dual, but a square lattice is self-dual. So we got, like this, we got this statement that the number of independent placate generator is L square minus 1. One can play the same game for the vertex case also on the dual lattice. And you get, like a constraint coming from when you multiply all the vertex generator. So you get one constraint from here. So you have L square vertex generators, and there is one constraint. So the number of independent vertex generator is L square minus 1. Okay. So basically, you see that I had L square minus 1 vertex generator independent and L square minus 1 independent placate generators. So the total number of independent stabilizer generator that I have is L square minus 1 plus L square minus 1. So that is 2L square minus 2. And we had just seen that our N is 2L square. And we saw the relation that N is equal to M plus K. So what is K? K is just N minus M, which is 2L square minus 2L square minus 2, which is 2. So that's why for Toric code, the number of encoded qubits that you have is basically 2. So you get K equal to 2 for Toric code. Okay, so I hope this makes sense. So now, we got, like the meaning of K. Now one can ask, like what is the D? Because we are in the stabilizer formalism. We talked about N. We talked about, like all these stabilizer generators, and then we talked about, like K. But we also need to talk about the distance D. So for that, if you remember, distance is the weight of minimal weight logical operator, and logical operator lives in the centralizer of the stabilizer minus stabilizer. So given the stabilizer group, you have to find the centralizer and then get rid of the stabilizer from there. And then whatever operators you are left with, find the weight of the minimal weight operator, and that will give you the distance. So we will do the same for the Toric code, and that will give us the distance of the Toric code. So we need to, because we have two logical qubit, we need to find, like on the first qubit, the Z logical operator and the X, and then on the second qubit, Z and X. And if you recall, what are the requirements for the encoded logical operator? I said just now, that the logical operator, I mean, based on a stabilizer formalism that we saw last time, must commute with all elements of the stabilizer group, which for us here are these vertex operator and the placate operator, must not be an element of the stabilizer group. So you should not be able to, get that by multiplying stabilizer generators. So it should be outside the stabilizer group and must satisfy the commutation and anti-commutation relation of the poly operators they encode. Like these are the things we need for encoded logical operators. So now this is very easy to, actually see here. So let's try to see, what will be the encoded Z operator. Now, an encoded Z operator should not be, should commute with, all the Z stabilizers, and that's not a problem because Z operators, they all, Z operators commute. So let's say you have Z1, Z2, Z3, and you take its whether Z2, Z3, Z4, and you look at the commutation, they will always commute. The problem comes when you have to look for the commutation between Z operate, tensor product of some Z operator with some tensor product of X operators. So Z and X is the problematic part. So what we want is that we need to form, let's say, a string of Z operators which should commute with, let's say, these placate operators and also, these vertex operators. But let's say you form any string. Let's say you form a string here. Now, obviously, this string will commute with your Z operator, but at the end of the string, you will have, you will have the vertex operator, and the vertex operator will, and it will basically anti-commute with vertex operator at the end of the string. So whatever string you have, at the end of the string, you will have some vertex operator, and those vertex operator will anti-commute, and we don't want it. And you can see that, like for example here, right? Let me use another color. So you are left with, like these ones, and here you are left with these ones. So here it anti-commutes and here it anti-commutes. So what happens that no matter what a string you take, regardless of its shape, if it has end, then at the end there is this, like adversarial X operator setting, and that is basically anti-commuting. So how should we get around this problem? The only solution is that you should not have an end. You should have a loop. So the only solution is to find a string of operators which has no end. And what kind of operators have no end? If let's say form a loop or something. So let's say if I just go around and let's say whatever, I don't know, we should maybe try to form a loop. Let's say this kind of operator. You can have direct loops also or whatever. But I can have two kinds of loop. I can have a trivial loop, for example. I can have a trivial loop, or I can have a non-trivial loop. Now, whenever I have a trivial loop, I will be always able to take placate generators and multiply them and get it. But you note that the operator that I have, the logical operator, it must not be an element of the stabilizer group. But any trivial loop that you form, so regular string is problematic because it will anti-commute with X. If you want trivial loop, that is problematic because it will be in the stabilizer group. You will be able to take product of stabilizer generators and you will be able to recover it. So it's in the stabilizer group. So the only solution that you are left with is having a non-trivial loop. So you just have a non-trivial loop and that solves the problem for you. So for example, it's very easy, like, for Z, you just take a non-trivial loop like this. Now, because there is no end, there is no bad X operator at the end generator to anti-commute with it, and it's not a problem. Okay. And once you have the Z logical operator, the X logical operator, easy to similarly find. You can take another loop such that, it cuts the Z logical operator at just one point. So let's say you take a loop which just intersect at one point, then it will satisfy. So you can take any kind of loop. You can take like this. You can take a straight loop or something. And why I want, you should just intersect odd number of times is because then I should write here maybe Z bar. These are the encodings of the Z logical operator and X logical operator. So let's say this is the Z logical operator, the non-trivial loop. Then the X logical operator can be taken something like this, because then it just intersect the Z logical operator at just one point, and then that will help you satisfy the anti-commutation relation. Because if Z and X intersect at odd number of points, then they will anti-commute. If they intersect at even number of points, then they commute. So for example, you can take a non-trivial loop, and the non-trivial loop can be like, very as long as it cuts odd number of time, it's fine. So let's say if you so for example, this is also fine, like what I have drawn, because then it will cut, like odd number of times. So this is your Z logical, this is your X logical on the first qubit. For second qubit, what you do is that this has to commute with X. So you can take any Z, like which has, let's say, even overlap with it or no overlap. And then the corresponding X will be, like you just take another non-trivial loop which cuts through it. So you see that, like these strings operator that, sorry, you can verify yourself and feel content that, by taking a string of operators which are along non-trivial loops, I am able to form, I'm able to form logical operators. So in this way, we get X logical operator and Z logical operator. And I said here that, right, that you can have more complicated operator also. Like you could have, for example, something like this. Actually, what you can think of them is that I have, let's say, have one operator and I have another operator. Actually, I can multiply them and I can get this kind of, this kind of operator. And why we have, this equivalent set of logical operator here is because, as I said, whenever you have operator L, which is a logical operator, and you have a stabilizer Sj, then L time Sj is also a same logical operator. So here, this non-trivial loop is a logical operator. This placket is a stabilizer. So when I multiply the two, because, this Z is, let's say, in common, so you get identity here. So then you are left with this object here. So that is also the same logical operator. You can even take, something like this. This is also a logical operator, because this is logical operator and these are like stabilizers. So you can get, 2 to the power m equivalent set of logical operators, because they're 2 to the power m stabilizers, and you can take LSJ as which it will represent the same logical operator. So, but then for code distance, we need to find distance of the shortest, like a smallest minimal weight logical operator. And when you do something like this, when you start making all these zigzag patterns and all, the weight of the operator increases. But what is the weight of the minimal weight logical operator? That is nothing but, like the length of this handle of your torus. So the shortest non-trivial loop, the length of that gives you the distance, because that is the weight of the minimal weight logical operator. And because we are working with, like L cross L lattice, like Toric lattice, the shortest non-trivial loop that we have, it has size is L. And hence, this will be the weight of the minimal weight logical operator, because logical operator is correspond to non-trivial loops. So we got n equal to 2L square, k equal to 2, and d equal to L. So that gives us, like all the thing. So I hope, like this makes sense to everyone. Anyway, this all will be recorded, is being recorded. So you can later see the slides and try to convince yourself. So the error correction via Toric code, I mean, this is also, again, in the stabilizer formalism, we can talk about it like, very easily. So we can detect errors on the stabilizer code by measuring the stabilizer generators, because I mean, as we saw last time, you just find the syndromes. And if let's say you get any -1, then you know that somewhere something has been messed up. And that tells you, that some error has occurred. And then by looking at this +1, -1, +1, -1 pattern of that, you can find, some error has happened. And syndrome, basically, we saw that it was outcome of the measurement of a given stabilizer generator. I mean, in the beginning, we talked about it. So whenever an error E happens, the stabilizer generator that don't commute with E will output -1. So let's say you have a Z error on a single qubit. So then there are two stabilizer generators that don't commute with it. And these are basically the vertex operators there. So which stabilizer generators anti-commute with it if you have a Z error on single qubit? Vertex operators immediately adjacent to it. So they will anti-commute and they will flag you that, oh, some error has occurred. Let's say more complicated pattern of error has occurred. Let's say this is the error. Let's say here there is an error here, Z, Z. Then there will be two vertex generators which are at the boundary of this string, which will anti-commute, and that will give you -1. You can have more complicated pattern of error. Again, the vertex generator which are at the end of the string, they will anti-commute because they will just have odd number of overlap. It's just one overlap, and that will give you -1. So you can have any pattern of errors. And when you measure your stabilizer generator, so let's say whenever you have a Z error, and when you measure X generators will give you, let's say -1, -1. Let's say, so here there is some X generator, here is some, and that gives you -1. So then you know that the error must be on the path connecting, these generators. So let's say, so here, for example, there is just one qubit, so it's okay. But let's say error has occurred, let's say here and here, then you know that, I mean, here it's simple because it's just one qubit. But let's say, for example, here, this has messed up and this has told you that, some error has occurred. So now you know that error is here and here, but it is a string of error. Now there are many paths which connects, like this qubit and this qubit. So you can, so for example, here the actual error was like this, and because it's a periodic boundary condition, it's like this. But then other possibility could have been like this. I mean, there can be many different possibility. And what people sometimes talk about is, they try to find minimal weight, among all those operators. So they are like these decoders. When we talk about it, we will see that given this pattern of errors, pattern of syndrome, you try to find what is the, error that has actually happened. So yeah, basically you just measure all the stabilizer generators, and the stabilizer generator will give you -1, and those stabilizer generator will give -1, which are at the end of the string of, let's say, Z error. So let's say you have a string of Z error, then the vertex operators at the end will give you error. And similarly, you can talk about X errors. In that case, the placates at the two end will give you the error. But we don't need to talk about like X, because if you're talking about Z, then the similar analysis you can do for the dual lattice, and everything will follow. So that's how you detect. So given any string of errors on the primal lattice, the only stabilizer generator have their outcome -1 or the vertices of that at the two end of the string. And for X error, you can do the same analysis. So that's how you detect errors. So you have detected some errors occurred. And here, in error correction, the main task is to identify the error operator so that, so let's say some error has occurred, and then you want to, in regular stabilizer formula, we say that, let's say if the error was E, then you just apply the same error operator, again, because polys are self-inverse. So that will help you. But you can even do, even more generally, because we are in the stabilizer formalism. So let's say if there is some error E, and if you apply with E prime such that E prime's time E is some stabilizer S, then that is also fine. Like this need not be identity, because let's say you started with psi, some error occurred, so you get E psi. Then you act with E prime. Obviously, if E prime is identity, then I psi is psi. But even E prime is, let's say, some stabilizer S, then S psi will also be psi. So if E prime is equal to stabilizer, where S is a stabilizer, then E prime will collect it. So let's say there is, like here you saw that, like these two vertex operators told you that they gave you minus. So you know that, like the error must be along, like the path connecting this qubit and this qubit. But maybe, like, yeah, I mean, basically, yeah, like, but maybe instead of doing, like the error correction along this, maybe, like you thought that you end up doing error correction like this by applying this operator. But in this case, it's not a problematic, because this was the actual error and this is what you did. The total action was basically a trivial loop. And because a trivial loop is a stabilizer, it's fine. It becomes problematic when, let's say, there is an error and you apply some you do something such that your action plus the actual error together forms a non-trivial loop. Then you will end up applying a logical operator. So we don't want that. So as long as this is the error and this is your correction, if together that forms a stabilizer, which is a trivial loop, you are fine. Okay. So more about this, like, I mean, we will cover when we talk about, decoders, because this is a very big problem, like a challenge. And that's why people try to develop better and better decoders, and they try to solve this problem and under different kind of assumptions. Okay. So this covers the error correction part. Now let's talk about Toric code Hamiltonian. So friends who are from condensed matter, like, I mean, they might have seen this book by Garvin and Young. And in 17.8, like they talk about Toric code Hamiltonian as an exactly solvable model of jet2 spin liquid. So it has some rich physics. So you can take all these X state generator and Z generator, and you can make the object like AS and BP. And you can, like sum over all these they can X generators and Z generator. Let's say this is, and make a Hamiltonian out of it. Yeah. And this Hamiltonian has, like rich physics. So yeah, I mean, we know that because, I mean, this we saw, right, that the vertex, this will commute, and these two will also commute, because X and Z, if they overlap at even number of qubits, then they commute. And for this Hamiltonian, if you look at the ground state, it has degeneracy 4, and like because it holds, like 2 qubits. Okay. So I will not go into detail about, this Toric code Hamiltonian, but, like if people are interested in condensed matter side, there's a lot of rich study of, Toric code Hamiltonian. So in summary, we talked about Toric code today, where we had, like Z stabilizers, we had X stabilizer generators, and they are not all independent. So there's a constraint. So you had L square minus 1 of this, L square minus 1 of this. And hence, this is because of those constraints, like you are left with 2 qubits. And distance was, like the weight of the shortest non-trivial loop, which was, like L. So we got this, and we talked about error detection, error correction. For all of that, we use the stabilizer formalism that we discussed in the last session. Then we talked about, this Toric code Hamiltonian. So I think that's it. In the next session, I think Andrew will discuss probably uh, Neal-Laflamme conditions and some of the theory of quantum error correction. And yeah, so yeah, I mean, you can join Discord and have discussions there and so on, and in the chat and all that. And I will try to share the annotated slides also later, maybe. So that's it. Yeah, thanks.
Yeah, okay. Thank you, Kishor. Thank you, everyone. And if you have any questions, you can post it through the Discord and some people can answer you. Yeah. So let's meet next week. Okay. Okay. Thank you, guys.